Another thing that I've heard you talk about related to underinvestment uh, in biological data is this idea that we don't yet know the scaling laws for biological AI. How much more data leads to better performance, across tasks, or
Mhm.
in the various tasks.
I think the debate is still out on this. You can look at recent papers, and there's some really good ones. But it depends on the domain that we're in, and certainly protein language models, they seem to scale better, maybe than some other ones, similar to large language models. Two examples I want to I think illustrate the way that I talk to customers and the way that we think about data coming in. So the first one is actually from Microsoft Research, and their academic partners. They just released a paper this month, and what it shows is that single cell foundation models, they don't follow scaling laws. So I think we're learning a lot more about what doesn't work than what does work. So it's still progress, maybe just slower progress, but this one's really interesting because we always think about single cell, or the field thinks about single cell as being maybe the epitome of good biological data that you can train on, because it's relatively easy to get large amounts of data. We're talking about 20, 100 million cells, lots of cells. Each one has multiple data points in it. You're measuring the transcriptome or the RNA expression in each of these cells. And it also allows you to have heterogeneity. And so, that's a really powerful thing in biology, because if we think about a tissue, that tissue, depending on the tissue, could have 6 or 20 or even more different cell types. And so having single cell methods has been revolutionary for biology. And I don't want to dismiss that. It's absolutely true. However, for modeling, it doesn't seem to be as performant as what you would expect. And so what this Microsoft research paper showed is that you can take 20 million cells for training, but your learning saturation actually plateaus around 200,000 to 2 million cells. That's a 1 to 10%. And then you don't get any benefit beyond that. I think this is a really surprising outcome for many in the field, maybe a little disappointing. But we'll talk about other methods that actually data points that we've been using that we really think are more exciting and probably more information rich that could help get over this saturation gap. But I think that's one example where maybe the biological scaling didn't allow for the AI performance that we would expect. Another one is in our own hands here at Datapoints, and that is, I mentioned we work on antibody developability. Now, antibody developability, through our best efforts, is still relatively expensive. You have to make the DNA, you have to make the protein, and then you start to measure these characteristics. We are actually making gains and improving the efficiencies of that, and I think there's some tricks, and we hope to announce some stuff very soon. But for now, we're talking about hundreds of dollars per antibody, right? So we test these, and we have one example where we have 250 antibodies, and we have some basic predictive models in that. You can learn on 250 antibodies, but we also have one that is 10 times higher of 2,500 antibodies. That allowed us to use some more advanced models like protein language models. We were starting to get into that big data paradigm, but we compared the performance of each of these models, one trained on 250, the other one on 2,500. What we found is that the improvement with 2,500 was not 10x better than 250. It was better, but not 10x better. I think this was a little bit surprising. However, we went back and we looked, and the catch is that the 2,500 antibody data set was actually less diverse than the 250. And this really points to an important decision-making step when you are designing data for training. And that is that it's not just the abundance of data, single cell being an example, antibody developability being another example. It's not just the quantity, it's the diversity of that data, and it's the types of the data that really matter.